Hi everyone, in this video we're going to start to talk about the next section of our topic which is called Atomic Absorption Spectroscopy, which is also known as AAS for short. Okay, so firstly what we're going to revise, or we're going to spend some time revisiting Bohr's model of the atom, because the Bohr model of the atom is really what helps us to understand how this particular technique works. And then we're going to look at a technique called atomic emission spectroscopy and atomic absorption spectroscopy. In the next video, then we're going to essentially look at how AAS works, so some of the mechanics of how we would use the particular instrument. Okay, so let's begin. So here we have an illustration, a simplified illustration of the Bohr model of the atom. Okay, so what we've got here, so we've got kind of three main areas that we're going to talk about. The first one, which I've simplified with this plus symbol in the middle, is the nucleus. The positively charged nucleus contains neutrons and protons combined together. We then have the presence of these electrons. Okay, so representing these dots that are orbiting around the nucleus. Remember that they're negatively charged. Okay, so positive nucleus, negative electrons. And so then the dotted or the dashed kind of circles in this particular diagram represent what we call energy shells. Okay, so remember that in the Bohr model of the atom that we consider that the electrons orbit around the nucleus in these energy shells, as opposed to just kind of all higgledy-piggledy around the atom. That they exist in these defined, so these energy levels. Now, in this particular atom, that it looks like planets around the sun. Remember, that was kind of the original concept of this model. We now recognise the electrons are more chaotic and random than that, so they're not like these defined kind of orbits, but it helps us to be able to picture what the energy shells look like. So this is kind of the model that we're working with. Okay, so what we're then saying with this particular model of the atom is that we're then saying that these electrons that are orbiting around the nucleus can move. They can jump from one energy shell to the next. Okay, so I'll clean this up and I'll simplify the diagram to show you the next bit. Okay, so what we have here in this slightly modified diagram, I've taken the same atom and I've added this extra kind of energy shell around the outside. Now you notice that, so this is representing a carbon atom because we have 6 electrons. 1, 2, 3, 4, 5, 6. But I've also shown this extra energy shell around the outside, which at the moment has no electrons in it. But what we can see is that what we see with this model of the atom is that when an atom absorbs extra energy by electricity, by heating, by being hit with certain wavelengths of light, what happens is that this, one of the electrons can be made to jump to the next shell. So I'll kind of show that sort of spot, which is where it might head. Okay, so we're absorbing energy to make this jump. Okay, and so then what happens is that it ends up being in this, what we call an excited state. So by the absorption of this extra energy, it's like you imagine, a Year 7 kid with 3 extra Red Bulls in the morning. Okay, that it's become excited. It's very an unstable, high energy state that is very short-lived. It can't maintain this for very long. It's unstable for the atom to be this way. So what then happens is that then we go from this excited state and we go back to the original spot we call the ground state. So we go from excited state to ground state, also by the release, in this case, of energy. So when we've gone from here to the excited state, we've absorbed energy. When we've dropped back down, we have emitted or released energy. And so what that energy is in the form of coloured light. So the reason that Bohr developed this model of the atom is that there was no satisfactory explanation for why atoms would release coloured light when heated or when excited by an electrical discharge. And so by being able to recognise that this jump between these two states, going up and then going back down, involves an absorption or emission of a specific colour of light or a specific amount of energy. So we can, I'll show you in the next kind of diagram another way that we can picture it. Okay, so here's an alternative way that we can visualise what's happening. So if we imagine that we have our little electron kind of at the bottom of this set of steps, or this well, basically. Okay, so this bottom position represents the ground state of this electron. Okay, so this idea that this is how the electron is normally existing, its normal amount of energy. Okay, so then what happens is that by absorbing energy, okay, so absorbing, it can jump up a step. Okay, so that we have a particular distance of this step. Okay, and we're just going to call it number 1. Okay, so we're absorbing energy to jump up to step number 1, and then we can emit it back again, or release it again, to go back the other way. So emitting. I appreciate it's getting a little bit cramped. Bear with me. Okay, but so the idea is that the distance of this step defines the amount of energy. So how high the step is, you can imagine, say if this were you, and you were in the situation where you were trying to jump up a step or down, the height of the step will dictate how much energy you need to use to get there. The bigger the step is, the harder it is to do it. And depending on how tall it is, you might stack it on the way up. Okay, but so then let's now, if I pick a different colour, what we can see here, I'm going to pick pink, is that we can actually go up to a different step. There is, in lots of situations, there's more than one possible step. So, let's say then I've got over here, I've got a distance number 2. Okay, so from this same ground state up to a higher step. So I can absorb energy, okay, to get up to step number 2, and then I would emit it back again to drop back down. So because number 2 is greater than number 1, that means that we've got more energy involved in jumping up to step number 2 and less energy, so there's more jumping up to step number 2 than step number 1, okay, because you're jumping up a higher distance. And so what we would get in this sort of situation is that we've got 2 different amounts of energy, one that's higher, one that's lower. And what we recognise is that in the atom, we get a number of these possible jumps that a given electron might do. Or, you've got atoms with multiple electrons, each of them can make a whole range of different jumps. And so what we see is that each jump corresponds to a specific colour. So each jump, to a specific energy, a specific wavelength of light that gets absorbed and emitted as we're making that transition. So what we see is that for a given atom, it will emit a number of different wavelengths of colour when all these possibilities are accounted for. Okay, and so then what we can do as scientists is that in recognising this phenomenon, we can then say, right, well, let's document what colours or wavelengths of light given atoms will produce. And so what we do is that we've documented it, and then we can use that information to be able to look for those particular elements. Okay, so in the next video we're going to start to talk about how we use this concept to be able to identify elements in a mixture, and then also to be able to use it quantitatively to work out the concentration of a particular substance. Alright, thanks for watching. Bye for now.